Hello everyone, we are presenting to you our COGS 118B final project, house price prediction. As we all know, the house price rise dramatically during recent decades, especially in urban areas. Our team decided to explore what kind of features of a house might be contributing factors of its rising price within a city. We picked the dataset based on houses in Amis, Iowa, from a Kaggle project named House Prices, Advanced Regression Techniques. We made use of machine learning techniques such as random forest, ridge and loss regression, and KNN on top of our own data processing. This is a link to our data source on Kaggle. About previous work from others, they took XGBoost method, which is an implementation of the gradient boosted decision trees algorithm. They went through cycles that repeatedly built models and combined them into an ensemble model. They also used neural networks to choose the best number of hidden layers and neurons and predict the house price. However, this method can be more complicated to implement. The target of our study is to predict the sale price of houses. From over 1,400 samples, we make use of both numerical and categorical data that spread over 81 columns with 79 features to study the price. Each column represents a house sample, and each row indicates a potential factor that may affect the house prices. However, what needs our attention is that there are a lot of missing data within this dataset. What we can see from the graph is that the labeled raw data is not strictly normal at the beginning. It is red skewed, where the skewness is 1.88. So we decided to do log transform for data label and get a pretty good result, which will benefit our model with the skewness close to 0.
Before analyzing the data, we need to pre-process the data for convenience. The most difficult part is to deal with the categorical data. To fit in the model, we need to convert categorical data into numerical data. The main method we use is one-hot encoding. For example, in the column of neighborhood, different samples may have different location. Overall, there are 25 locations. So we build the location feature vector with length 25 for each sample. If this sample belongs to this location, then we mark the corresponding column 1, otherwise 0. And we do the same thing for other categorical features. Another challenge is to deal with the nums. Since some columns of original data frame may contain num, we need to convert it into none for convenience. Basically, we will use 3 methods to solve the problem: the regression, k-nearest neighbors, and random forest. The most intuitive way to predict the house price is using regression, because the job is to predict a real number with many numerical features. All numerical is due to the pre-processing. So we decide to use ridge and lasso regression to solve the problem. First, we will talk about a ridge regression. Ridge regression also uses the least square loss function, but the difference between ridge regression and simple regression is that ridge regression has a regularization term with parameter lambda. This term is the product of lambda with the sum of square weights, which is the L2 norm. L2 represents the square. The purpose of regularization term is to prevent the model from overfitting. However, the regularization term will increase the complexity of our model and decrease the accuracy. So we need to use cross-validation to choose the most appropriate model, with 80% for training and 20% for validation. Also, we used k-fold method with 5 folds to choose an appropriate parameter lambda to balance the accuracy and the complexity. After several experiments on the choice of lambda, such as 0.1, 1, 10, and 100, we find out that 10 gives the best performance. The plot on the right shows the relationship between the parameter lambda and the performance. The curve reaches its peak at lambda equals to 10. After training, we apply the model on the validation set, and the traditional true mean square error is huge. There are several possible reasons for these huge results. The first is the scale of the target, which is the range of house price. The original house price is relatively big, such as 200,000 something, so the mean square error is huge. The second is the imbalanced feature vector, because the original dataset includes many categorical data, and we preprocess all of them with one-hot encoding. Also, the large mean square error may be due to the small sample size, and the model is not robust to the outliers. However, this model is pretty good because from the R-squared score, this model can cover almost 86% of the data. Then we want to compare lasso regression with ridge regression. Lasso stands for least absolute shrinkage and selection operator. Lasso also has a regularization term. However, the difference is that the regularization term is the absolute value of weights, which is the L1 norm. One of the advantages of lasso regression over ridge regression is that lasso is robust to outliers because the absolute value. Another most significant advantage is that lasso can do the feature selection. The original dataset has 79 columns, which means 79 features. After preprocessing, we have around 300 features. Among them, there are some meaningless features, and lasso can get rid of them and select only useful features. Still, we use cross-validation to choose the appropriate parameter lambda. After training, lasso selects 111 useful features and eliminates 177 features. Among these useful features, the above around area by square feet has the largest positive coefficient. That makes sense because the living area is greatly related to house price. And the most negative coefficient may represent the most unrelated features. The property lambda is 15 from the left plot, and from the right residual plot, the residue is around 0 after normalizing, so the model gives a good performance. The mean square error of lasso regression is still huge, with similar reasons to the ridge regression. Lasso can cover around 86.9% of the data, which is slightly better than the ridge regression.
K-nearest model is a straightforward way to predict house price given a specific house. The basic idea is when we get the information of a house, we start to find the most similar house in the training data set by the similarity function cosine similarity. After we pre-processing the data, we use the panda get dummy to encode the whole data set. This building method makes the category string into 1 and 0. For example, if one cell shows that the house is at the south or north part of the city, after we use get dummy, the south become 1 and north become 0. One hot encoding is necessary for us to do the cosine similarity. Right now the data is all 1 and 0 and some int values. We use log to access the whole row and use toList to make this row to a list of float numbers. When we access one house from the test dataset, for example, ID number 1, we loop through the whole training to find the 20 most similar houses in the training dataset. Since Kaggle does not provide the testing set for us, we have to use the training test split to evaluate our predictor. In order to say the R-squared score for K-nearest model, we take the average of price of most 20 similar houses as the prediction price for the house. The R-squared score is around 0.66. This is pretty low because the way we determine the price of the house is take the average. It is obviously not as accurate as regression, so this K-nearest model is only able to find the interval but not to predict the accurate price.
And then we choose to use random forest model. Random forest is a meta estimator that feeds a number of classifying decision trees on various subsamples of the datasets and use averaging to improve the predicted accuracy and control overfitting. Also, random forest won't be influenced too much by the correlated data, because random forest address this correlation by choosing the one predictor among a random subset of the predictors at each split in each tree. Here's a heat map, and it presents features related to sale price. We can see that some features are highly correlated, but random forest can still be used for this dataset and become a very proper model for house price prediction. Typically, random forest methods encourage two ways of handling missing value. Drop data points with missing values, fill in the missing value with median for numerical value, or mode for categorical value. We do it both. We check the missing ratio of the dataset and find out 4 features have more than 30% of data missing, which can be a really critical structural problem. Thus, we delete these 4 features and fill in another with median value if numerical and mode if categorical. After everything's set, we begin to train our model. We use random forest regressor with different parameters to try. We choose to do it with replacement because of the relative small dataset. Then use k-fold and grid search CV to find out the best parameter to choose for prediction. We found out that the max depth should be the 15, and we use all the features for best splits. Number of trees in the forest should be 500, which means we take weighted average of 500 decision trees. After knowing the best parameters, adjusting the models, and getting the predictions, it's time for result evaluation. For a regression model, our R-square score is a proper measurement for the performance of the data. It stands for how much proportion of the data can be explained by your model. We calculated R-square score is around 0.887, which is a really good feedback. Besides, we calculated MSE, a standard error score for prediction, and got 0.19. It looks very small and good. It kind of makes sense because not only our random forest model can control our feed and have a good generalization, but also we do data preprocessing and log transformation. Last but not least, L1 norm are calculated for supplement test. All measurement shows that our model works and do good job. And here's a summary for 3 models and their R-square scores. The regression got 87%, the KNN got 66%, the random forest got 88%. Here's the pros and cons for the 3 models. Regressions predict exactly numerical value and easy to implement, but is quite influenced by the correlated feature. KNN is easy to implement and time-saving. However, when facing predicting an exact number, R-square score is very low. Random forest is has good generalization and controlling overfitting. However, it's hard to implement and fails when facing rare outcomes. And here's a discussion. We want to know how to improve the performance of a single method. For regression, since we convert many categorical data into numerical data, this kind of transformation has some impact on the model. If we can think of a better way to process categorical data, we may improve the performance of our regression model. For the KNN, we think our predictor might be overfitting. Because we use scale price to compare the cosine similar, so we delete the sale price column when we train our model. For random forest, how to find the best parameters for the best prediction is a question, because random forest is computationally expensive and need more time to run. In addition to improve one single model, we also want to know of a way to combine several methods together. This new stack mode may give better performance. And here's the reference and citations. Thanks for watching.